There is a date already marked on a calendar inside NASA. It has not been announced to the public. It has not made the news cycle. Most of the scientists who know about it are sitting quietly with what it means, because there are no adequate words in the English language for it that don't sound like exaggeration. On November 18, 2026, at 16 minutes and 12 seconds past 2 in the morning, Pacific Standard Time, an object will cross a threshold that no human-made machine has ever crossed. It will be so far from Earth that a signal traveling at the speed of light will take a full 24 hours just to reach it. You could send a message on a Monday morning and not receive confirmation it arrived until Wednesday. That object is not new. It was not built this year, or last decade, or even this century. It was assembled by hand in a California factory using technology that predates the personal computer, the internet, and the mobile phone. It was designed to last 4 years, maybe 5. It launched 49 years ago, and it has never stopped moving, never stopped listening, and never, not once in nearly half a century, stopped talking to us. Right now, as you watch this, that machine is sending data back to Earth from a distance of more than 15 billion miles, a signal stretched across more empty space than anything our civilization has ever reached, carrying information about a region of the universe that no instrument, no telescope, and no scientific model had ever been able to directly observe before it arrived. And what it has been telling us in recent years is something that NASA scientists are describing in very careful, measured language. Words like unexpected, words like inconsistent with our models, words like requires us to reconsider. Here is the part the headlines are not telling you. The strangeness of what this machine found is not just scientifically significant. It raises questions about the invisible shield protecting every living thing on this planet, and about how much of the universe sitting just beyond our reach has been quietly behaving in ways we never anticipated and never detected. This is the story of Voyager 1, and the most important part of that story is still happening right now, in 2026. This is Deep Space Declassified. We take the real discoveries that science buries in journals and technical reports, and we tell the full story. If you want to be here every week when we open the next file, subscribe now and turn on notifications. Let's go. September 5th, 1977, Kennedy Space Center, Cape Canaveral, Florida. A Titan III rocket lifts off carrying a spacecraft called Voyager 1, the size of a small car, about 1 ton in weight. Its onboard computer has less processing power than the calculator sitting in your kitchen junk drawer, less than the key fob for a modern car. Its mission, as NASA outlined it at the time, was specific and modest. Take advantage of a rare planetary alignment that occurs only once every 175 years. Use the gravitational pull of the giant outer planets as a slingshot. Fly past Jupiter, fly past Saturn. Take photographs, record measurements, transmit them home. Then drift into space and go quiet. Sometime around 1981 or 1982. 4 years, 5 at the very outside. Nobody in 1977 seriously believed Voyager 1 would still be functional in 1991. The possibility that it might still be operational in 2001 would have been called wishful thinking, and the idea that in the year 2026, 49 years after launch, it would still be transmitting real scientific data from a region of space that no one in 1977 could have imagined it reaching would have been dismissed as science fiction. But before we get to the anomaly, before we get to what Voyager found out there that broke the models, you need to understand one more thing about this spacecraft, because it carries something that has nothing to do with science. Attached to the outside of Voyager 1's frame is a 12-inch gold-plated copper disc, a phonograph record. On that disc are sounds, greetings spoken in 55 human languages, the song of humpback whales, the sound of rain on a forest, a human heartbeat, 90 minutes of music drawn from cultures spanning the full recorded history of human civilization, from Bach to Beethoven to Chuck Berry to a pygmy initiation song recorded in Zaire. Astronomer Carl Sagan, who helped design the record, described it as a message in a bottle thrown into the largest ocean imaginable. It was assembled for whoever, or whatever, might one day intercept this drifting machine and want to know who sent it. That record will still be traveling when the sun burns out. It will still be traveling long after every city we have ever built has been erased by geology and time. It is the most permanent thing our species has ever made, and it is attached to a machine currently running on 4 watts of electricity. Stop and let that land for a second. 4 watts. The small light inside your refrigerator uses more power than that. The nightlight in a child's bedroom uses more power than that. The most important scientific instrument in the history of human exploration of space is running on less electricity than a votive candle produces in heat, and it is still going. To understand what Voyager 1 found, and why it matters, you need to understand a piece of geography that most people were never taught in school. The solar system does not end where the planets end. Neptune is not the edge. The Kuiper belt is not the edge. Even the Oort cloud, the vast theoretical shell of distant comets that may extend almost halfway to the nearest star, is not the true outer boundary of our solar neighborhood. The real boundary is something you cannot see, cannot touch, and cannot photograph directly. It is defined not by distance but by pressure. Our sun does not just produce light and heat. It constantly releases a stream of electrically charged particles called the solar wind, flowing outward in every direction at speeds approaching 1 million miles per hour. That solar wind inflates a massive bubble in the surrounding space, a region scientists call the heliosphere. Think of it as the sun's sphere of influence, a cosmic force field generated not by technology but by the star itself. Inside that bubble, the sun's particles and magnetic field dominate everything. Every planet, every moon, every asteroid, every comet, every spacecraft we have ever launched, and every living thing that has ever existed has spent its entire existence inside that bubble. The outer edge of that bubble, the point where the solar wind finally exhausts itself and gets pushed back by the pressure of interstellar space flowing in from the other side, is called the heliopause. The heliopause is the real, physical edge of our solar system, the line between everything we have ever called home and everything we have not yet explored. And in August of 2012, 35 years after it launched, Voyager 1 crossed through that boundary and came out on the other side. It became the first human-made object in the entire history of our civilization to leave the solar system. Think about what that actually means. For the entire span of human civilization, every war ever fought, every empire ever built, every discovery ever made, every person who has ever lived and died and been remembered, all of it happened inside a bubble defined by the reach of our sun. And in 2012, for the very first time, something we built escaped that bubble. But confirming the crossing was not as simple as reading a number off a dial, because the one instrument specifically designed to directly measure the plasma density outside the heliosphere, the plasma spectrometer, had failed in 1980. 3 decades before the crossing, the most important sensor for this exact moment had gone permanently dark. So scientists had to get creative, and in early 2013, the sun handed them a lucky break. A massive solar eruption sent a shock wave rippling outward through space. That shock wave traveled for over a year before it finally reached Voyager 1 at 15 billion miles away. When it arrived, it caused the surrounding plasma to vibrate, like striking a tuning fork in a silent room. Voyager's plasma wave instrument picked up those vibrations. By measuring the frequency at which the plasma oscillated, scientists could calculate its density. The number that came back was unmistakable. Voyager 1 was no longer surrounded by the hot, thin plasma of the solar wind. It was embedded in the colder, denser plasma of interstellar space. NASA made the announcement in September 2013. Official, peer-reviewed, confirmed. Voyager 1 had become the first human-made object to enter true interstellar space, the space between stars. A region of the universe that, until that moment, existed for humanity only in theoretical models and educated guesses. And then it started sending back data from inside it, and that data did not match any of the models. Here is where the story shifts, and I want to be precise about what I mean when I say shifts, because this is not a story about something exotic or inexplicable. It is a story about something much more unsettling. Proof that some of our most fundamental assumptions about the universe directly surrounding us were wrong. When scientists analyze Voyager 1's plasma density readings from just outside the heliopause, they were not working from guesses. They had decades of rigorously peer-reviewed theoretical models describing what the interstellar medium in our region of space should look like. These were serious models, developed by serious physicists over 30 years. Models that had been tested against every available observation and held up against scrutiny consistently. Those models predicted a specific range of plasma density for the interstellar space immediately surrounding our solar system. When the numbers came back from Voyager, they were significantly denser than that range. Not slightly off. Not within a reasonable margin of error. Significantly denser. The first instinct was to check the instruments. When you are working with hardware that is 4 decades old, built before the invention of the personal computer, operating at temperatures and radiation levels it was never designed to withstand, and it gives you a number that contradicts 30 years of theoretical work, the reasonable assumption is that the hardware is wrong. Engineers checked. They cross-referenced readings. They tested for calibration drift. They looked for every possible source of equipment error. The data held up. Then, in November 2018, Voyager 2 crossed its own heliopause. Moving in a completely different direction than its twin, having traveled through the outer solar system on a different trajectory entirely, arriving at the boundary from a different angle. And Voyager 2 still had a functioning plasma spectrometer, giving scientists a direct measurement rather than an inference from vibrations. Voyager 2 found the same thing. 2 spacecraft, 2 completely different directions of travel, 2 different sets of instruments using 2 different measurement approaches, the same unexpected density at the boundary, the same surprising sharpness in the transition. That ruled out equipment error. That ruled out a localized anomaly. Whatever was happening at the edge of our solar system was real. It was real on both sides, and the models had missed it. But the density anomaly turned out to be only the beginning. Here is the part of this story that most science coverage glosses past. Because the heliosphere is not just a scientifically interesting feature of our solar neighborhood, it is a shield. And what Voyager found raises questions about that shield that have not yet been resolved. Interstellar space is not a gentle environment. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent events across the galaxy, stream through the space between stars at significant fractions of the speed of light. These are not the kind of particles you want bombarding living tissue. The Sun's magnetic field, carried outward by the solar wind and forming the heliosphere, deflects and scatters a substantial portion of that radiation before it reaches the inner solar system. The heliosphere does not protect us from everything, but it filters out enough that combined with Earth's own atmosphere and magnetic field, the surface of this planet is livable. When Voyager's instruments logged the cosmic ray count as it crossed the heliopause, the numbers jumped dramatically. The transition was not gradual. The protection does not fade over a long distance like the edge of a fog bank. It cuts sharply, right at the boundary, like stepping through a doorway and finding yourself in a completely different climate. Now add the density anomaly to that picture. If the interstellar medium pressing against the outside of our heliosphere is denser and more complex and more turbulent than every model has accounted for, then our understanding of how stable the heliosphere is over geological timescales needs to be reconsidered. We are not talking about a threat to life on Earth tomorrow, or in a century, or in 1,000 years. We are talking about timescales relevant to the long history of evolution on this planet. We do not yet know what a more turbulent external environment means for the long-term behavior of the heliosphere over millions of years. But we now know we were missing something real and confirmed, something that was out there the whole time, and that our models simply did not correctly describe. And then, just as scientists were beginning to take that seriously, Voyager 1 found something else, something quieter, something continuous, something that, once found, could not be ignored. A hum. In May of 2021, a team of researchers led by Cornell University astronomer Stella Koch-Ocker published a paper in Nature Astronomy that changed how scientists understood the space beyond our solar system. Ocker's team had gone back through years of accumulated data from Voyager 1's plasma wave instrument, the same sensor that helped confirm the heliosphere crossing, and found something buried in the background that no one had specifically gone looking for. Not the sharp, sudden signal from a solar shockwave, not a one-time event, something completely different. A faint, narrow-band signal, persisting continuously in the background, month after month, year after year, barely changing, just there, quietly, the whole time. Scientists call it plasma wave emission. What it represents physically is the natural electrical vibration of interstellar plasma itself. The thin gas between the stars is electrically charged, and those charged particles are in constant motion, oscillating at a frequency determined by the density of the medium. That oscillation produces a faint but measurable electromagnetic signal. In a very real sense, interstellar space has a tone, a hum, a continuous, measurable frequency generated by the space between the stars, carrying within it information about the density and structure of the medium producing it. Before this discovery, scientists could only take isolated measurements of interstellar plasma density during specific triggering events. Those solar shock waves that reached Voyager once every few years, each one a single data point, the next one years away. Like trying to understand the weather across an entire continent by checking one thermometer once every 3 years. The persistent hum changed that entirely. For the first time, scientists had something closer to a continuous feed, a live, ongoing signal from inside interstellar space, updating as Voyager moved through it day after day, revealing in real time what the space between the stars actually felt like from the inside. And what that signal showed was almost more surprising than the hum itself. The density of the interstellar plasma was not constant. It fluctuated. Subtly but measurably, it rose and fell as Voyager drifted through the medium, which meant interstellar space was not the featureless, uniform void that generations of scientists had assumed. It had texture. It had structure. A complexity and variability at scales ranging from meters up to millions of miles, completely invisible to every telescope and theoretical model built from the surface of Earth, because until Voyager arrived, no instrument had ever actually been inside it. Oker herself was careful in how she framed the significance. This was not, she said, a case of space being broken. It was a case of space being more alive, in a physical sense, than the models had assumed. Nothing about this hum suggests anything artificial or exotic. It is entirely a natural, physical phenomenon. But natural does not mean ordinary. And this particular natural phenomenon required rewriting what an entire generation of astrophysicists had been taught about the region of space directly surrounding our solar system. And just as this research was gathering momentum, just as scientists were beginning to use the hum as a real-time measuring tool to map the structure of nearby interstellar space, something happened to Voyager 1 that very nearly ended the mission permanently. November 2023. Engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, noticed something wrong with the incoming data. Voyager 1's signal is still arriving. Part of that story is still happening right now, in 2026. This is Deep Space Declassified. We take the real discoveries that science buries in journals and technical reports, and we tell the full story. If you want to be here every week when we open the next file, subscribe now and turn on notifications. Let's go. September 5th, 1977,